Hi everyone, my name is Kaiwen Zhang, a PhD student from University of Washington, and today I will introduce the Gallium framework, which enables automated software middlebox offloading to programmable switches. Recent progress in programmable switches allow developers to implement customized packet processing logic using the P4 programming language, which is an easy-to-use programming interface. It has been shown by various previous projects that offloading middleboxes to programmable switch can improve its performance and save CPU cycles. However, this requires manual effort and deep understanding of the switch model. Our goal in this project is we want to be able to automatically offload existing middlebox implementations. To be more specific, we would like to offload part of the middlebox functionality to a programmable switch that is directly attached to the middlebox. We would like to use this programmable switch to perform pre- and post-processing for packets. Ideally, we would also like to find fast paths in the middlebox, where the middlebox server can be completely bypassed and packets can solely be processed by the programmable switch. Of course, performing automated offloading is not easy and there are several challenges. The first one is that we need to guarantee the functional equivalence between the offloaded version and the original middlebox program. Because in the offloaded middlebox, the packet is being processed by both the P4 program running on the switch and the C++ program running on the middlebox server. Therefore, we need to guarantee that when these two programs combine together, its behavior is equivalent to the original middlebox program. The second challenge came from the fact that the offloaded code have to conform with all the constraints of the programmable switch. These constraints include the expressiveness constraint, where certain operations, such as integer multiplication, cannot be performed on the programmable switch. The offloaded code also needs to conform with resource constraints, which come from the fact that certain hardware resources are limited on the programmable switch, such as the total amount of memory. The third challenge is that we need to make sure that the offloaded program is concurrency safe. This concurrency comes from the fact that the programmable switch and the middlebox server will be processing packets in parallel. This additional parallelism will change the program behavior. Therefore, we need to provide a run-to-completion semantic to make sure that packets still appear to be processed by a single device. Through the rest of this talk, I will first introduce the design of the Gallium framework, which uses dependency analysis during the partitioning to guarantee the functional equivalence of the offloaded middlebox. It also considers both expressiveness constraint and resource constraint during the partitioning to make sure that the offloaded code generated by Gallium conform with all the restrictions of programmable switches. It also uses atomic switch state update and delayed packet release to provide a run-to-completion semantic. We then evaluate the effectiveness of Gallium's offloading approach by conducting a case study that involves 5 input middlebox programs. We study what is being offloaded by Gallium and can Gallium actually give us any performance benefits. The very first step of Gallium's workflow is that we need to perform a dependency analysis on the input middlebox code. Dependency analysis is important because for two programs, if all the operations that depend on each other are executed in the same relative order, then these two programs will have the same behavior. If two operations depend on each other is getting reordered, then the program's behavior will get changed. In Gallium, we mainly consider two types of dependencies. The first one is data dependency, where two operations access the same state and one of them is a write operation. This includes cases such as read after write, write after read, and write after write. The second type of dependency is control dependency, where the result of one operation determines whether the other operation will get executed. A good example of this is the computation of a conditional variable that will be used later in the branch. After performing the dependency analysis, Gallium will generate a dependency graph, which is a directed graph of operations. This dependency graph will then be used in the partitioning process. In the partitioning process of Gallium, the middlebox code will be partitioned into 3 stages: the pre-processing stage, the middlebox server stage, and the post-processing stage. During this partitioning progress, there are several requirements that have to be met. The first one is that we need to meet all the dependency constraints. This means that operations could only be placed on the same stage or stages after their dependencies. As a concrete example, let's now consider operation A and B, where operation B depends on operation A. Now, if operation A is partitioned to the Middlebox server stage, then operation B can only be placed on the Middlebox server stage or the post-processing stage. B cannot be put on the pre-processing stage because by doing so, you will reorder the execution order of A and B, therefore change the behavior of the program. The second requirement is we need to met all the expressiveness constraints. This means that the offloaded code, which are the code that is being partitioned to the pre-processing and post-processing stage, can only contain code that can be supported by the programmable switch. The last requirement is we need to met all the resource constraints, which means that the offloaded code does not exceed the resource limitation of the programmable switch. Now, in order to meet the dependency and expressiveness constraint, Gallium will first perform a labeling algorithm that assigns labels to each operation. These labels are used to denote all the possible partitions each operation can belong to. The labels include pre, post, and CPU, which corresponds to the pre-processing, post-processing, and the Middlebox server stage. So, to start the labeling algorithm, Gallium will first initialize all operations with all labels. It will then look at each operation and see if it can be performed on the programmable switch. If it cannot, then we will need to remove the pre and post label from the operation. For example, an integer multiplication operation will have its pre and post label removed. After that, Gallium will then consider the dependencies between operations, and based on this dependency, it will further remove labels, and this will run iteratively until no more labels can be removed. To give a concrete example, let's now consider the following Middlebox implementation. This is a simplified version of a load balancer, where it will first use the source and destination IP address to compute a hash value. This hash value will then be used as a key to perform a lookup from a flow table. If we found an entry in the flow table, it will then use the result to perform a packet rewrite and send the packet out. Otherwise, the hash value will then be used to pick a backend server, and we will insert a new entry to the flow table and rewrite the packet. Now, in order to assign labels to each operation in this program, Gallium will first initialize all operations with all the three labels, pre, post, and CPU. After that, we will consider whether each operation can be performed on the programmable switch. For example, on the programmable switch, we cannot perform integer division and table insertion. Therefore, for these two operations, they will have their pre and post label removed. Gallium will then need to consider the dependencies between each operation. For example, for these three operations, because it depends on operations that can only be assigned to the Middlebox server stage, therefore, these operations cannot be put on the pre-processing stage and have to have their pre-label removed. Similarly, this operation's result is being used by a table insertion, which can only be placed on the Middlebox server stage. Therefore, this operation itself cannot be put on the post-processing stage and have to have its post label removed. Note that Gallium will need to perform this label removing following dependencies iteratively until no more labels can be removed. After the labeling algorithm finishes execution and all the labels are determined, Gallium will then use this label information to assign a single partition to each operation. For operations with a pre-label, it will be assigned to the pre-processing partition. For operation with a post label but there's no pre-label, it will be assigned to the post-processing partition. And operations with only a CPU label will be assigned to the Middlebox server partition. So, going back to our running example, we will use this label information to determine which partition each operation belongs to, and this will naturally partition our program into three pieces. Now, we've got an initial partition that considers both the dependency constraints and expressiveness constraints. However, during the process, we did not consider resource constraints. To satisfy all the resource constraints, Gallium will further remove code from both the pre-processing partition and post-processing partition until all the resource constraints are met. During this process, Gallium will consider the following list of resource constraints: the total number of operations on a single execution path, the size of the global states being assigned to the programmable switch, the number of temporary variables being used during the process, and the size of the accurate header space required to transfer intermediate results from the programmable switch to the Middlebox server. After doing this code motion and make sure all the resource constraints are met, the partitioning process will generate 3 pieces of program. For these 3 partitions, they will satisfy both the dependency, expressiveness, and resource constraints. However, these are not enough to guarantee the correctness of the offloading. This is because that when processing packets, the programmable switch and the Middlebox server will be running in parallel. Such additional parallelism will change the program behavior. Therefore, in order to make sure that the offloaded version have the same behavior as the original Middlebox program, we will need to provide a run-to-completion semantic. This means that processing of a packet should appear to be completed before moving on to next packets. This requires us to make sure that later packets should not be able to observe partial updates resulting from previous packets. To provide this run-to-completion semantic, Gallium uses 2 different mechanisms. The first one is that Gallium will buffer the packets and delay its release to the network until all the updates to the switch state is being reflected on the programmable switch. This ensures that packets that causally depend on each other should always be processed using the updated states from the previous packets. The second mechanism being used by Gallium is that Gallium will batch the updates to the switch state and perform all the updates atomically. So, instead of directly update switch states on the fly when processing the packet on the Middlebox server, Gallium will first batch all these updates and wait until this packet is being fully processed by the Middlebox server. Then, Gallium will perform all the updates atomically so that they appear all at once on the programmable switch. In order to provide this atomic update, Gallium will create a write-back buffer on each of the tables on the programmable switch. Gallium will first write all the updates to the write-back buffer, but at this point, the write-back buffer is not available to be used by the programmable switch. Then, Gallium will perform a single bit flip to inform the programmable switch to use the result of the write-back buffer. Therefore, it makes all the updates available all at once to the programmable switch. Of course, using this mechanism, it is still possible for later packets on the switch to be processed using an older state. But we argue that this does not violate the run-to-completion semantic because such scenario can only happen on packets that are causally unrelated to each other, and therefore it will be equivalent to an in-network packet reordering. These 2 mechanisms that guarantee the run-to-completion semantic will be provided as a runtime system. Now, the final step is to perform a code generation. Gallium will need to generate P4 source code that can be deployed on the programmable switch from the LVM IR, which is the IR we choose to use during the dependency analysis and partitioning process. In order to do so, Gallium will first need to convert the control flow graph of the LVM IR into a sequence of pipeline stages using its topological order. Then, it will split each individual basic block from the control flow graph into smaller code snippets where within each code snippet there's no dependency between the operations. This is necessary because P4 requires that each pipeline stage does not contain code that depends on each other. After that, Gallium will perform a line-by-line translation from the LVM IR instruction to the corresponding P4 operations. Gallium will also need to generate header definitions for all the temporal variables being used during the process of packets. After the code generation, we will get a switch code in P4, a server code in C++. These 2, combined with the runtime system we mentioned before that provides a run-to-completion semantic, is the final offloaded version of the input Middlebox code. To evaluate how effective is Gallium's offloading mechanism, we will now perform the evaluation that consists of case studies that using 5 different Middleboxes as the input to Gallium. We will try to answer the following 2 questions. What is exactly being offloaded by Gallium, and how can Gallium provide any performance benefits? To understand what is exactly being offloaded by Gallium, we use 5 different Middleboxes as input to the Gallium system. This includes a NAT, a load balancer, a firewall, a transparent proxy, and a Trojan detector. For all the 5 Middleboxes, we will manually inspect the P4 code and the C++ code that is being generated by Gallium and see what exactly is being offloaded. We find that for all the 5 Middleboxes, Gallium is being able to offload at least one lookup table. such as the address translation table of the NAT. We also find that during this process, Gallium is being able to find a fast path in all the 5 middleboxes where the packet processing can be solely performed by the programmable switch without the involvement of the middlebox server. To understand the performance benefits provided by Gallium's offloading, we will now use several macro benchmarks to measure both the throughput and latency of both the offloaded version and the original version of all the 5 middleboxes. During this process, we find that to achieve the same throughput, the offloaded version could be able to save from 21 to 79% of CPU processing cycles. In terms of latency, we find that the offloaded version can reduce up to 31% of latencies. We find that all of these performance benefits came from the fact that Gallium is being able to detect a fast path in the offloaded version. Therefore, the packets can directly be processed by the programmable switch. We also evaluate the performance of the offloaded version under a more realistic workload. Here, we choose to use the enterprise and data mining workload from the Conga project. Both of these workloads consist of a mixture of short and long flows. We find that to achieve the same throughput, Gallium is being able to save from 3 to 81% of processing cycles. We also find that Gallium's offloaded version will perform better for workloads with longer TCP flows. This is because when processing packets in the longer TCP flows, more packets can be processed by the fast path, therefore bypass the middlebox server. In conclusion, here we introduce the Gallium framework, which can automatically offload the middlebox implementation to a programmable switch. It guarantees functional equivalence between the offloaded version and the original version. It considers the expressiveness and resource constraints during the partitioning progress so that the generated offloaded code can conform with all the constraints of the programmable switch. It uses atomic switch state update and delayed packet release to guarantee the run to completion semantic, so the additional parallelism from the fact that the middlebox server and the program switch is running in parallel does not affect the program behavior. We also applied Gallium to 5 example middleboxes and show that Gallium is being able to detect fast paths that bypass the middlebox server for all 5 cases. It can save from 21 to 79% of processing cycles and can reduce the packet latency by up to 31%. Thanks.